So we are going to discuss first order system transients, specifically exponential decay. Okay, and this is pertaining to the GATE biomedical paper. So let me explicitly write that. We are going to look at this from a GATE biomedical exam syllabus or paper point of view. Okay, exam syllabus or paper point of view. Okay, which subject does it belong to? Is a very hot question. Okay, because are there first order systems in, let's say, human anatomy and physiology? Answer is yes. Are there first order systems in biomechanics? Answer is yes. Okay, or there is a first order system, this exponential decay, does it show up in biomaterials? Again, the answer is yes. Okay, and will they show up in other things? Medical imaging, how about that? Answer is yes. Okay, so you name a subject, that is how important this particular topic is. Okay, and almost every year there is one question based on first order systems from 3 or 4 of these subjects. So from, say, let's say 4 subjects, one question each, there are about 4 questions in the GATE examination. So bioinstrumentation, and to a large extent even circuits. You can pretty much name all the subjects in engineering mathematics. Okay, differential equations, this topic is there in all of them, including electronics and controls. That's what makes it so important. Okay, having said this, so we are going to look at this from a biomedical exam perspective. Does that mean, is it not useful for students, non-biomedical students, instrumentation, electronic students and all that? No. Okay, I already point out certain topics here: circuits, electronics, controls, okay, measurements. So the same ideas also show up in many other engineering topics. Okay, that's one thing. So having said this, if I have to put this in one specific subject, what would that be? That would be bioinstrumentation. This is where you are using ideas from pretty much all of these topics. I missed S and S. Technically, it also should be there. Okay, signals and systems, circuits, measurements, electronics, controls. Okay, in knowledge of medical imaging, biomaterials, biomechanics, plus knowledge of human anatomy and physiology to make measurements from on the human body. So I would rather put this in this. If I have to choose one topic, it's going to be bioinstrumentation. Okay, and it's certainly useful for branches too, and it's highly efficient to discuss in one setting rather than looking at them in a piecemeal way in individual subjects. Okay, so that's why we are having this session, special class right now. Okay, so useful for other branches as well. Okay, having said that, so here is a quick overview. So what is this first order transients? What is this exponential decay that I am referring to? Equation form, typically in data and behavior form, how does it look? Okay, and then we'll also look at how this equation is showing up. The underlying differential equation is one of the basic differential equations. Okay, why is this equation so ubiquitous? Because this underlying differential equation models the phenomena in all of these subjects. Okay, the same differential equation. So solution of that is going to show up again and again and again. So what is an underlying differential equations? And then importantly, okay, there are few details about some of the parameters that need to show up. Let's understand that. Typical problems that they ask here. There is not one specific thing they can ask. They can ask things in many ways. What are the things that they can ask? And here, okay, you said it's useful in HAP. Can you give me an example? Let's say useful in biomechanics, biomaterials. Again, can we look at examples? Okay, so we look at examples from most of these topics. Okay, and then typically time constant is a fundamental parameter, but depending on the conventions and the subject, there are many. The same parameter is slightly modified and used in different contexts based on conventions. Okay, for example, medical imaging, the parameter goes by a certain name. Okay, in biomechanics goes by a different name and all that. Do this, and I have scheduled 2 hours, so we likely have time to look at it. Okay, this is a starting point. Where does this go? What are the generalizations, right? And what are the generalizations? And here I also need to mention, if you're looking at typical problems, let's say atypical problems, also look at that. So if you understand this one bit clearly, there is about approximately 10 marks in the entire gate paper. Okay, 10 marks, about 4 to 5 questions in the entire gate paper will be based on this one topic. There specifically we are looking interested in transients, right? Plus things or functions of time. Things or functions of time. And that specific function that we are interested in is the exponential decay. Okay, it has this specific form. It decays with respect to time, e power minus t by t. Okay, so the basic exponential decay equation is this. Okay, we have pick any parameter variable of interest in the problem. Okay, this variable, depending on the field, this variable is different. Okay, I'll give some examples a couple of slides down the line. This variable is a function of time, variable a, but we are not used to calling a as a variable. Let me just call y as a variable. Y is a function of time. This function decays exponentially in time, so this is e power minus t, and typically it starts decaying from an initial value. Okay, and the decay rates is controlled by a time constant tau. If I have to plot it, how this looks is, quickly let's see some of the things. So y0 is initial value. Use this color. Y0, this is initial value. How do we know that? Y of t is a function of time, right? Let's calculate what is y of 0. If you substitute it in the RHS, when t is 0, e power minus 0 is essentially 1. E power 0 is 1. So only this constant remains. This happens to be y0. You're starting at y0. Then as time increases, this is time axis, this is y of t. Okay, the variable of interest. As time increases, e power minus t, that becomes smaller and smaller. Okay, it becomes smaller and smaller. It also exponentially drops. So it doesn't go like a straight line or a polynomial. It kind of exponentially drops like this. And it kind of touches, asymptotically touches 0. So at any other time t, the value is y of t. This height is y of t, and that happens to be e power, this happens to be y0 e power minus t by. Okay, y0 is the initial value. Y0 is this initial value, the starting value, the starting height here. Whatever height you are starting from, it kind of exponentially drops. This exponential function minus t. What is this tau? Tau do? Tau goes by the name time constant. Time constant changes how fast this curve to 0. It can either go slow or it can go, can go really fast or it can go very slow. For example, I have 3 curves. Say you have parameter tau2 here. Let's say this corresponds to parameter tau1, and this corresponds to parameter tau. Can we quickly rank parameters tau1, tau2, tau3? I'm also writing them, it's either tau1 greater than tau2 greater than tau3, or it's the other way around. We are presuming continuity with respect to how this this function behaves with respect to this parameter. That is, it doesn't like go down and then suddenly increase while increasing the value of tau. Okay, so tau2 and let's say tau3. Can we quickly say which one is the highest here? Which one do you think is the highest? Tau is, so middle value is tau2. Okay, some value, let's say 1. If it is less than 1, will it drop fast? Or if it is greater than 1, will it drop fast? In fact, notice this itself is a starting possible question. Can you rank the parameters, order of the parameters from the figure? Okay, one is to make a guess. Side by side, we can also quickly, I think we can easily plot it. So let me also go to most, start plotting this. Okay, get a set of points. So let's see what this function is. F of x is e power minus t or minus x. Going on here is, we are looking at an exponentially decaying function. Let's zoom this a bit. See where this initial point here at time t equal to 0, the value, the coefficient is 1, right? So we are starting from there. Let's add a slider for that coefficient. The starting value is, let's say, a0. Okay, let's add a slider for that. What does that do? If you change that, initial value is going to be, whatever you specify that to be. If you raise it, it starts decaying from a higher number. For example, 2, starts at 2 and starts decaying. Okay, you can raise it, the initial value, all of them. Notice, look at the values along this line. Okay, right now is at 1.6. You can change this 1, 0.5. Can it be negative? Yes. Can be minus 0.5. Whatever is the initial condition, starting from there, kind of going towards the 0. In fact, for the time being, let's just stick to what happens to the positive side. The coefficient here is a positive number. Let's also put the parameter tau there, the rate of things. Let's call it P. Add a slider for P. Yes. Okay, now we have smaller time constant, faster decay. Smaller the number of B, okay, larger is this 1 by B. So faster decay. That is one explanation given. And then, so in the figure that I shared, notice tau 1 should be really large, decay is very slow, 1 by that is very small. Okay, so right now tau 1 greater than tau 2 greater than tau 3. Tau 3 is the smallest, 1 over tau 3 is the largest, it decays the fastest. Let's also put that in words. Smaller the tau. Let's not worry about grammar or let's not be a grammar nazi. Smaller the tau, larger is 1 over tau. Okay, so faster the decay. That is, if the coefficient of minus t, if it is large, decay is fast. Faster the decay. Okay, does that happen? I put a slower. Let's say this is 1. I increase that, it should decay slow. Being slower. If it's very large, almost it's becoming a straight line. The range of interest, right? If this make this parameter, the tau there is the B here. Okay, so compared to 1, now make it smaller, decay is faster. It's almost like we'll stop at 0. Okay, again for this class, what happens if we make the time constant negative? That's an interesting question. Then this is not a decay anymore. E power minus, right? This minus and that minus cancels. Let's not worry about it in this class. So let's keep B in the positive value. So this is like instantaneous change, tau 0 change possible. Then decay slows down as he keeps on increasing the parameter. We can see that. If you want, in fact, if you want me to show comparatively, let's put here, let's call this 1. Compare the 3 functions. Okay, let's have 2 more functions. F2, make tau 0.5. Let's make this, and let's compare it with respect to 1. If you increase the parameter, the green curve, this is slower decay. If you decrease the parameter, you get a faster curve. Okay, the curve or faster decay. Color is not good. Perhaps if you want a slightly contrasting color, yeah, there you go. Tau is smaller, there is a faster decay. Typically, tau can be positive and negative. It's an interesting question, but for now, let's make sure all the taus are greater than 0, so that we are looking at decay. This is, let's say, this is strictly greater than 0. Okay. Equality, there is an instantaneous jump. In fact, you are getting a interesting function. Now, exponential decay and exponential saturation go hand in hand. Let's also look at what that is, and we can do this relatively fast. Okay. So here, so let's say this is y of t, right? Starting with some y naught that we have studied so far is this curve. This is time t, the height is y of t. That decays exponentially, that we have seen. Often, this height is also of interest. Let's call it by another name, okay? If we call this y1 of t, we can call this another variable. You could call it z of t, okay? Let's call it, let's say, r of t, okay? R of t, what kind of a function is r of t? Notice this is just the total height subtracted, y of t subtracted from the total height. Total height is a constant, right? So this is nothing but y naught initial value that you subtract y of t, that is r of t. So your r of t equals e naught minus y of t. You can have a few things, intermediate steps. Y of t, is y naught e power minus t by tau. Okay, your r of t happens to be y naught into 1 minus e power minus t by. If you look at y of t, it was initially very large. It keeps on decaying. If you look at r of t, this is initially very small, keeps on increasing, but kind of saturates, right? That is, its maximum value is y naught. How do you know that? You can quickly make a couple of checks here. Notice r of 0. If t is 0, this is 1. 1 minus 1 is 0. R of 0 is 0. It starts with 0. what is r of infinity or r of t tending to infinity? T tending to infinity, e power minus t is 0. You get y naught. So r keeps on increasing, kind of saturates at y naught. So if you had to plot that, just r of t, it kind of looks like this. Here we have plotted y of t, right? Plot r of t. Starts at 0. Maximum it goes till y naught. Kind of saturates to y naught. Stage A, this is how charging of a capacitor works. Yeah. This behavior, for example, seen in electrical circuits. Okay. So there is exponential and exponential saturation. Now let's quickly cut to the chase. What are the typical problems they can ask? Typical problems. Let's take this decay equation. Perhaps I want to show both, what happens in both the scenarios. So let me split the page. Notice your y of t is not e power minus t by tau. The other case, let's say r of t is y naught minus y naught e power minus t by tau. Let's look at this case first. There are 4 things that are related here. The time, initial value, constant, y of t. 4 things here. Of t, value at time t, initial value, time, the time constant. There are 4 things. E is a constant, right? Fixed. One relation among these four values. A particular time, this is a value. At a given t, y of t is a value. For example, give me a time. Time is 1, time is 2, 1.5. Y of t is a value. Right? Given, so these 4 values are kind of connected. Typically what they do is, given any 3, find the other. Given any 3, given 3 in this set, find the other. The type of problem. How do you find? So given 3 are given, how do you find it? This equation is also easily solvable. It not only shows up again and again and again in many places, it's also easily solvable. Okay. How do you solve this? Okay. Take ln on both sides. Okay. So you have ln y of t equals ln y naught minus t by tau. 3 values are known. Find the other. For example, if y naught is known, t is known, tau is known, you can substitute in the RHS, find what is ln y of t. Okay, from that you can find the y of t. In fact, to find y of t, you can just substitute here, right? Let's say if y of t, y naught t is given, right? These 3 are given. You can find tau. If you write, slightly rewrite this is nothing but, notice, t by tau happens to be ln of y naught minus y of t, right? You can write it as ln of y naught by y of t. Or if you're quickly wondering where that change happened, okay, ln of y of t. In other words, your tau happens to be by ln y naught minus ln y of t. Equation you can easily solve for tau. Notice when I wrote this down, I am actually referring to a very, very, very large class of problems. And any 3 in this set, you can find the 4th one. Questions? What I have shown. This equation is also easily solvable. This is also easily solvable. Again, notice, given any 3 in this set, t, y naught, tau, r of t, right? Given any 3 here, this set, and find the other. And quickly, how do you solve this? If you take ln on both sides, in a way, this parameter tau is hidden in the power. To undo the power, you have to take ln on both sides, right? If you rewrite this, okay, y naught e power minus t by tau happens to be y naught minus r of t. Okay, this is a value, this is a value, not again, this is a value, this is a value, this is a value. One of them perhaps is an unknown. Let's say tau is an unknown. Okay, if you take ln on both sides, you have ln y naught minus t by tau equals ln of y naught minus r of t. So given 3, you can find the other. For example, if tau is unknown, you can calculate this value, you can calculate this value, you can calculate the difference, you can calculate this ln, right? The time you can actually, you have 3 constants and tau in the denominator, you can easily solve for it, just like this equation. There, this is like a corollary, right? Simple modification of that. Problem, essentially one and the same. Okay, here you're looking at y naught e power minus t by 2. Y complement of that, right? Y naught minus y naught e power minus t by 2. A typical problem. Okay, quick question. Can you think of examples of this kind of system, exponential decay or saturation system. In fact, if you think of decay, one of the variables, if you think of one of the variables, there is always a related variable that will be a complement. Okay, so can you think of this exponential decay in some of the gate biomedical topics that we have seen? For example, can you think of any applications of this? It shows up in HAB this way, it shows up in biomechanics this way, biomaterials this way, medical imaging this way. Can you at least think of one example from each of these topics? So preferably if you type in, right, others should pick a topic subject that is complementary. For example, Shamayata typed in suture decay. This is from bioinstrumentation. So this is taken. Okay, biomaterial. If you prefer still stick to biomaterial, you need to tell me a slightly different example. Okay, not again suture decay. Can someone else pick biomechanics, for example? Stress, relaxation, and cartilage. I'll put that in biological tissue properties. Okay, viscoelasticity, biomechanics. Okay, it shows up in biomechanics. Where else? So some of the things that we have seen in class so far, right? Biomaterials, biomechanics. How about medical imaging? How about bioinstrumentation? I'll also do the easy one. Circuits, RC circuit, resistor capacitor circuit, charging of a capacitor, right? LR circuits, RC circuits, the most classic example. Fine. Come on, quickly, any other examples? Okay. While I am waiting for an example, let's go back there and look at few things. Okay, I don't need this comparison graph. I don't need this graph. There is a point over there. B is a slider. Let's have a list of points. Okay, let's make it a list. Make it from 0, 0.1. Just go till 2.5. Time constant in this one. Let's see what these numbers are. Hey, come on. Right now I have only 2 examples. I gave, circuits. Okay, RC circuits. Let's plot. Let's first look at this, the values of this. Okay, a collection of points. 0, 0.1 goes till 2.5 of points. In fact, let's see these points. I have here is, let's make this, notice the collection of points I have here is 0, 0.1, 0.2, 0.5. Divya Prabha says radioactive decay. So medical imaging, radioactive decay. We have 10 spect. There is radioactive decay, right? Let's look at the function is f of x, right? Of p. Initial value is 1, I suppose. I'm leaving a naught at 1. The time constant b is also at 1. Oh, this is also plotted here. Great. Notice the set of points are all kind of plotted. Let's take out the initial condition of that. Let's also turn off that continuous curve. These are the set of points. They are chosen points from 0 to 2.5. Okay, let's have that function. Controlled drug delivery systems. Okay, that's actually interesting example. Okay. So with respect to saturation, can you control the amount of drug in the blood? Let it not spike, sudden change, but gradual changes, but at the same time, you want to maintain the drug level at a certain value, right? Controlled drug delivery, fine. Actually, a fair example, but more involves both control systems and biomaterials. Okay. Now let's look at few points. One thing is, I already said, notice the typical problems that show up here is of this format. Given any 3, find the other. Okay, but there are certain points in time, certain values of y out t that are specifically of interest. Okay, for example, typically we are used to gathering data and we are dealing with this curve. Let's say we are dealing with this curve, exponential curve. Okay, from the curve we are expected to estimate what the time constant is. So often there is a necessity to deal directly with the curve, not with, given any 3, find the other. I'm going to give you the curve, or equivalently, I'm going to give you a set of data points. From there, you have to extract me what the tau is. Okay. Linear regression, we know how to do. Perhaps you take ln on both the sides. Do regression after taking ln. Perhaps you could do that. But I will also show you how to infer value of tau from this figure, or if a set of data points are given. Okay. Now we have some medical imaging. Someone says MRI signal T2 relaxation. How about T1 relaxation, right? T2 relaxation, okay, fair example. T2 relaxation, T1 relaxation. Immunity response Again, these are the typical immunity response is not a first order system, but fair. Okay, now you're thinking of differential equation. How about bacterial growth? Okay, bacterial growth in a culture, tissue growth in a culture. Perhaps it has this exponential saturation, right? Or you're looking at, you have a antibacterial drug, you have a certain amount of starting bacteria concentration, you put the drug and look at how the concentration drops. Typically that is exponential decay. In the sense, immunity response, fair. There are some aspects of immunity response, you could say, any first order kinetics be modeled here. Okay, so this is a typical problem, right? What are some atypical problems? One is, given this figure, can you tell me what the time constant is? Given a set of table, can you tell me what the time constant is? Let's look at this value. So I have from 0 till 2.5. Time points are 0 to 2.5, increasing by a del t of 0.1, interval of 0.1, equal intervals, right? Starts at 1, becomes 0.904, 0.818, 0.74, and all that. Something interesting happening here. Okay, let's plot, perhaps let me plot that point. This is 1 comma 0.368. Plot that 1 comma 0.368. Yeah, there is something interesting about this green dot. Want me to zoom in? I could also do that. There is something interesting there. Anyone spot something very interesting about the green dot? In fact, there is something interesting about this number 0.368. 0.37, let's say, in fact, let's make it 2 decimals, the discussion 0.37. That's interestingly, what is left is 63% has decayed, only 37% is left. In this is starting with 1, 0.37 is left, so 0.63 has already decayed. Okay, what is special about it? There is something interesting happening with this number 0.37. If you start at 1, if you are at 0.37, something interesting happen. Make something change, or let's change the time constant. Make it 2. 1, I am making it as 2. Okay. Again, let's look at the set of data points. At 0.37, you have something interesting happening. Let me again plot that point. Okay. Time 2, you have 0.3, approximately 0.37. Notice from 1 it becomes 0.37. This is specifically interesting. Interesting about that point. Okay, let's change b back to 1. If b is 1 at 0. Notice these are all at the same height. Value 0.37 is what matters. Perhaps if we want to do that, let's do one more intermediate value. Okay, 1.5 perhaps, to show that things are in a straight line. And it is 0.367. the time point is 1.5. what is happening? 0.37. Notice 0.37 constant, it's always occurring at the 0.37. Something interesting is happening. Can anyone spot it? No, b is at minus 1.5. b is 1, something is happening at 0.37. b is 2, again something is happening at same 0.37. What is that? Can anyone spot? 63% have decayed. What is left is 37%. Time corresponds to the time constant, tau. Notice time constant is 2, right? At that time, 37%, what is left is 37%. When time constant is 1.5, what is left is 37%. Starting with 1, right? We'll also change that and see. Starting at time constant is 1. What is left is, when 37% is left, the corresponding time is a time constant. Okay? I am not going to half-life yet. I'm just like, from the figure, you can find what the time constant is. We need to go to related parameters, half-life, we'll go there yet. What I'm saying is, you have a curve like this, experimental curve like this, see the percentage change. Whenever the change is decreases 63%, or what is left is 37%, that time gives you the time constant. You don't have to take ln on both sides, look at 2 points. You can actually get it from the figure. Is the first non-typical thing that they do. This is, so given any 3, find the other. Given a figure, find the time constant. Yeah, let me actually show that. Time constant from data. Okay, the starting value need not be 1. Okay, starting value can be anything. Let's say let's start at y0, and it kind of decreases. So notice your y of t is y0 e power minus y tau. What is the value of y when t equals tau? T equals tau and time equals one time constant, what is y of t? What is y of tau? Let's find it out. Okay. Notice y of tau as y naught e power minus tau by tau power minus 1. So this is essentially y naught by e, or y naught e power minus 1. Okay, e power minus 1 is essentially y naught by y naught. I'm going to, again, it helps to see this way. E into 1 over power minus 1. What is 1 over e? Can someone quickly tell me what that value is? 0.378. There is actually 0.3678. Okay. Notice y naught into 0.367. Again, this is important. So let's get it in color. Notice this is 0.3678. 4 decimals. Yeah, 3678. 3678 or 79. Doesn't matter. 78. Y naught. Put this in simple English. Value t is tau. Value at t is tau is a fraction of the initial value. Fraction initial value. Initial value is y naught. There is a fraction of that. Also say this corresponds to 37% of y naught. Fraction ratio, it's, as a fraction, this is 0.367. To 2 decimals, it's 0.37, right? That is 37% of y naught. What is left is 37%. Is y naught. This value is y naught. What is left is small fraction of that, 0.37 of y naught. You are essentially looking at tau. Time that corresponds to that is essentially tau. So given a set of grid lines, hey, 63% is happening here, 37% is happening here, right? Given a set of grid points, you can technically read out the time points. They will also make sure this point intersects with one of the reads so that you can actually read out the time points. This is one way they can ask you for value of tau given a figure. A grid, you can actually read out the clear. So again, what they are doing is this: given 3 things, find the other. But they can give you a figure and ask you to do the same. They want to slightly easier. This is so easy. They can ask you more lines in the grids. Fine. Let's also look at this thing. Notice. So how much it dropped from the top, the changes decreases. What is left is 37%. Decreases 63%. So you can read the value of tau given a figure, given sufficient resolution there, you can actually read the value of tau. Is it clear? I'm not solving for tau essentially. I'm just noting it. Whenever 37% is left, that time corresponds to tau. They can give you a figure to actually read it. There is one more way to read this from the figure. But before I go there, let's also, I asked you a question, okay, which are the topics that shows up, right? There is one more way to read it from the figure. Go there, but before that, answer, where it typically shows up. Biomechanics we recently did, right? There are some cartilage properties, for example, use a time-dependent mechanical response. We do creep recovery and stress relaxation studies. So in viscoelasticity, we have Kelvin-Voigt, and Maxwell model, right? There this shows up. In fact, the time constant would be equal to eta over E. You have sigma is eta epsilon dot. This units of Pascal. This is 1 over time. This is Pascal second. This is RHS's units of. This is Pascal. This is Pascal second. So you get Pascal, or sorry, second. Right? The time constant, corresponding time constant is typically eta over E. Many of you mentioned immune response, radioactive decay, right? Tissue culture, bacterial growth, tissue growth. Typically any first order kinetics, including radioactive decay, shows up, okay? In terms of degradation, when we're talking about something like weight or density is degrading over time. Some of the properties like composition of a mixture is degrading over time. Okay, density again is changing over time. Strength is not a good way to write it, but let's say strength is decreasing with over time. Take a suture, degradable suture, its strength is decreasing. Right? Stretch an aorta, hold it, do an experiment. Right? It's the force you need to hold it at a stretch position keeps on decreasing. It's getting easier and easier. This is known as stress relaxation. Right? So all those places. So any property as a function of time, number of side chains in a polymer. Side chains keep on getting cut. Okay, might be the reason for degradation, underlying degradation in strength or density. Okay, any property as a function of time. Typically, this is seen this way: E of t. Any property of t, property that as a function of. Classical example is this: circuits, RC circuits. You have tau is RC, or you have here tau is L over R. You have a single resistor and capacitor in series or parallel, doesn't matter. There is one time constant, that is RC. Charging of a capacitor, discharging, right? Or if you have an inductor and resistor, the behavior is the same. Someone pointed this one thing out. You have MRI magnetization, specifically T1 and T2 relaxations happen this way. Now, many things in bioinstrumentation or applications of circuits. Defibrillator, you're essentially charging a capacitor and then discharging it when you defibrillate. It's an RC circuit. You're charging a capacitor and decharging it, defibrillation. Same goes with pacemaker. The way to apply a current impulse is to actually discharge a capacitor, charge and discharge a capacitor. You have a timing circuit to change the circuit, switches to change the circuit. But the underlying thing is there is a capacitor that discharges. Electrodes you'll see learn again, it will be modeled by as a simple RC circuit. So this tau is RC is how we are going to model many of this important components of these systems. Electrodes at this stage, I also need to say even PZT, piezoelectric crystal. The simplest models, reasonable model is a RC capacitor model. The crystal. Many sensors, in fact, if PZT is a RC capacitor model, many other sensors actually would be a simple RC circuit, either a current source or a voltage source with a resistor capacitor. Most sensors are this. I have put up respiration, breathing, ventilator. Can anyone make that connection? MRI magnetization T1, T2. Let's say MRI magnetization T1, relaxation T2, relaxation. Respiration, breathing, ventilator, this shows up. Ventilator. Notice you have a simple RC circuit, a series circuit, then parallel circuit. Already seen this in biomechanics, right? Notice airways, trachea and all that has a resistance for airflow. Lung is compliant, it's capable of changing its volume, right? Not only flow can be stored or volume can be changed, right? The lung compliance. One of the simplest models there, you're having a spirometer and trying to see how fast is the exhalation and all that. You're essentially again dealing with exponential drop during exhalation, forced expired volume or expiratory rate, any of that, how much, 10 to 90%, how much time does it take, right, for the volume to be expired. That again is an exponential decay. Is a very good approximation because you essentially have a resistance for airflow and capacity to store volume, change volume, store and discharge volume. So there is airway resistance and then lung compliance or lung capacitance. Okay, for I'm using the term for reach or to make it approachable. Okay, airway resistance, which is why, in fact, if you're breathing through your nose and your mouth, you're changing impedance, you are changing the resistance. So you are changing how fast you are inhaling or exhaling. You are essentially changing the time constant of the system, right? Respiration and breathing. Okay, these are closely related. Okay, same reason you have a ventilator. You are dealing with there is resistance for airflow, then there is capacitance for storage of airflow, storage discharge of air. It's almost like you have a voltage source, you are charging and discharging that capacitor, or you are like ventilating the air and pumping air and getting it out. Again, aspects of the ventilator can be studied with this. In HAP, in fact, bioinstrumentation will quickly start discussing this. Model for a nerve cell, right? Nernst potential and all that. You have the potential, you end up with a simple RC circuit for lipid bilayer, the membrane, cell membrane. Here, almost, this is a cell membrane, okay? This is the outside of the cell, this is inside of the cell. Inside, outside. Then there are some channels, so there you need either a current source or something like that, okay? Typically, you need a current source or something like that, but again, it boils down to an equivalent resistor capacitor model. This is slightly involved, but again, nerve cell, the starting model is a RC model, okay? The way calcium, not calcium, calcium is secondary, right? Sodium, potassium, chlorine, exit and enter can be modeled this way. simplest first order model. Okay, sometimes you need diode and all that to make it more realistic, but this is a starting model. In any3 you can find the other, and that equation, that solution shows up almost everywhere. This way there are at least 4 to 5 questions in the entire gate paper. In fact, if you look at sensors, thermistor, there is an exponential drop in resistance with respect to temperature, right? There are many other things in sensors I already mentioned, right? Analog electronics diode model, a good reasonable model for a diode is it's actually, this is an exponential model. Okay, either current flow after the threshold, okay, current is infinite, or you make this almost exponential. Okay, so again, in analog electronics, the diode model has this, it's not a decay, the parameter there is positive, but the equation is essentially the same. So this shows up in almost most topics in the syllabus. Let's get back here. So they can ask a question from any of these topics, and typically circuits, they are typically going to ask this. You ask a question in biomechanics or tissue biodegradability, tissue culture, you're going to ask this. Drug delivery also, you can actually typically frame a question to follow first order kinetics. Okay? So they can give a figure and ask you that, or they can also give you a table. In that sense, hey, notice, yeah, we showed it. Starting with any y naught, t equals to what is left is 0.367 or 37%. Okay, you could also see that in the table here. Now let's go change that y naught. Let's make it 2. Okay, our time constant is right now 1. So 2, what is 37% of 2? 0.37 into 2, roughly 0.74. Okay, notice when it is reaching 0.74, the value is reaching 0.74, or you are touching the time constant. This point where I have the arrow pointer right now, right? Roughly this is 0.6, 0.7, between 0.7 and 0.8, close to 0.75, right? You have one time constant. It's only the percentage change that matters. Okay, that's one thing. Now there is also a different way they can ask. You could actually read the value of the time constant in a very different way here. Does anyone know how to do that? Y of t equals y naught e power minus t by tau. For that, let's look at where is this thing, what is the solution of? Let's differentiate this and see. Okay, dy by dt is y naught is a constant minus 1 by tau y naught e power minus t by. Notice essentially dy by dt is minus y by tau. This is the governing differential equation. Whenever you have differential equation of this form, you're going to get this as a solution. Let's also read this, interpret this. Rate of change is proportional to the current value. Negative of the current value, it's proportional to the negative of the current value, right? It decreases. The higher it is, the faster it decreases. The higher it is, the faster the decrease. The moment it becomes smaller, it decreases slowly, right? The value is bigger, the value, the faster the drop, right? So this exponential self-referential decay is there in that, the bigger it is, the faster the decay. That is the underlying language, simple English for this equation. That shows up again and again. Taller you are, bigger the fall, right? Higher you go, bigger the fall, something like that. Hey, the taller I am, higher the climb, right? That also makes sense. So the proportionality constant here is 1 over tau. Okay, proportionality constant is 1 over. Rate of change is proportional to current value, proportional to negative of value. Fine. Ask me how do you read the time constant from this figure? It so happens this initial slope here corresponds to the time constant. You draw a tangent initially, wherever this touches the time axis, that will be the time constant. Why is that the case? Let's take this. Okay, y by dt. Let's evaluate it. In fact, let's use this color itself. Y by dt is an initial slope that is at t equals 0. This minus y naught by. So I'm going to color code it so that you can see the relation clearly. This is minus decrease the negative slope. Notice initially the slope is negative. Y naught is positive. Let's say tau is positive. Okay, you have y naught by tau. Have y naught by tau, actually describing the slope of this drop. If you plot an initial tangent wherever the initial tangent hits the time axis, initial tangent hits the time axis exactly at tau. Exactly. Notice the slope is y naught by tau. And it's negative, right? That's why we have the initial slope is minus y naught by tau. So they can be talking about fractional change, specifically 37% change, give you a figure that shows where that happens and ask you for the value of time. They can also, make it easier for you to draw the tangent and, ask you for the value of tau. Typically, they do this. Given any three, find the other. This is the most typical. If they want to slightly, one question here or there, this is what they are going to do. The third thing is, notice this 37% change, whatever is being given as a figure can always be given as a table. We have also seen that, right? Given a table like this, set of points, time and value at that time, we can always see where the 37% change is happening. That will correspond to the time point. For example, let's make the initial value, let's make it 1.5. Where should the change happen? Can the table, which value should I read? Can someone say? Initial value is 1.5. Corresponding to which value will be the time constant? Start at 1.5, it becoming some other value. Small fraction of 1.5. The fraction or fractional value. 0.555. I get one answer in the chat. 0.5 into 0.37 approximately 0.555. Let's see. So the time constant still remains the same, right? The time constant here B is one that still remains the same. 0.555 corresponds to the time constant one. So they can give you a table, and based on the fractional change, you can actually read the time constant. There's one more way they can slightly change the question. So typically they can ask you, give you data in table format, figure format, equation format. You can do that. Or, given any three, find the other. Given t in this set, tau, y naught, of t in the other. This is possible. They can give you a table with, let's say, 37%, 37% either remaining or 63% decrease. You can get the time constant from there. They can also give you a figure. The figure, you can either do initial slope. If it's a gridded figure, you can get, time at 37% remaining on. Then they can also ask you for related parameters. So sometime, someone mentioned, is this related to half-life? Yes, this is related to half-life. Instead of asking you the time constant, because if you know the time constant, you know the half-life, say of radioactive decay or bacterial decay, you can actually talk about the half-life of that parameters. Half-life. Okay, we'll just show half-life here. Other things show a summary of that. Again, so you have t starting with y naught, you have y of t. Y of t equals y naught e power minus t by tau. Now the question is, when does this y of t become half? When is y of t equals y naught by 2? Notice, answer to this question by definition is a half-life. By definition, it's half-life. This is half-life. Let's write it as t half. How is t half related to tau? Let's do that, okay? So your current y of t value is naught by 2 equals y naught e power minus the time is what we are trying to find. So this is actually by definition, this is t half by tau, okay? So you have half, ln of half equals minus t half by tau, plus half equals ln 2 into tau. Not y naught cancels. What you're left with is half. Take ln on both sides. Ln of 1 by 2 is minus t by 2, t half by tau. By definition, I am writing t half there. Okay, you can take this negative to the side, it becomes ln 2. So t half is essentially ln tau into ln 2. So this is, be careful how you read it. This is tau into ln 2. What is ln 2 value? Can someone quickly find that also? This t half we have here as half equals 0.8. This is different from 63%. This is 0.6. It's a fraction of tau. This fraction is 0.693. Okay, be careful about this number. Sometimes there is this confusion between 63% and 0.693. It's better to remember ln 2. Okay, if they want to slightly play with you and do this, given any 3, find the other. Okay, they could also do this. 1, 3, t, tau or t half. So if you give me one, I can find the other. Okay, find the other. T, find the other. Either this or that is given. That is also possible. Okay. So far, what I have tell you, I mean, whatever we discussed, if you know that clearly, if you know all the applications, you have seen that you know actually what happens in T1 relaxation, T2 relaxation. If you know pretty much what happens in most of these applications that I mentioned, okay, you are very good. In fact, if you know that, you know some basics of non-biomedical subjects in GATE syllabus, as well as you know some advanced things in biomedical subjects. The first order systems being that, you know, the important thing that I always mention. So you are at this stage, you are not worrying about clearing the cutoff. You are actually, can I like do well? Can I try to get a good seat of my choice and all that? That's a category that you are in. And it boils down to notice at the end of the day, it's the same thing. It's a 2-hour discussion. Okay, there isn't a lot to memorize or recall. That is how important this is. But some of you might want to go one more step, right? You want to excel in the GATE exam. So what are that we did not discuss? I'll mention those things and we will, you know, wind up. We looked at dependent parameters, but there are also dependent variables. There is a capacitor charging and discharging. What is the energy dissipated in the resistor? You're talking about energy or power. That is a dependent variable. There is a dependent parameter like T half. You have a defibrillator circuit. What is the power consumed in a defibrillation, right? Need not be RC circuit. Can be a defibrillator circuit. Capacitor discharges. The load is so much during defibrillation. Resistive load is so much. Can you tell me total energy dissipated or power as a function of time, right? So you can talk about dependent variables. Let's say in RC circuit. So when I say RC circuit, it, you know, RC is showing up everywhere, right? All the applications. So you can talk about energy and power in most of those applications. Say showing up everywhere. RC circuit is the base of all this: defibrillator, pacemaker, electrodes, ventilator. If you are careful about the units, right, you can also, what is the power consumed, how much energy actually required to perform this action of metabolism, how much energy is wasted during respiration, right? You can also start answering some of those questions if you are very, very careful about the units. So dependent parameter like T half that we discussed, or it can be a dependent variable like energy or power, that is possible. And notice, so the equation that we looked at, the underlying differential equation that I derived, right? Dy by dt 1 by tau y equals 0. The equation that we saw is dy by dt plus 1 by tau into y equals 0. This right hand side, you can have what is known as a forcing function, x of t. Because x of t is 0. On the own, the system decays, but you can apply an external voltage or external force that is time varying. What happens in that case? Have a forcing function. Typically, a step function, bare minimal heavy side, you know, step function is a bare minimal thing you need to know. You know, sometimes you also do impulse ramp. 3 things typically discussed, and that is where, of course, we have this. What I say is dy, you know, this is the equation that we studied. We studied as dy by dt plus 1 by tau equals 0. This RHS need not be 0. There can be some function in the RHS. That is what we have studied so far in, you know, in simple terms, is just initially the capacitor is charged and this is discharging. What will happen to the voltage and current in the circuit? That is a problem that is studied. What, when we say we have a forcing function, there is a voltage source there, right? And this voltage source need not be a, you know, constant. It can be a time varying function, right? So the RHS there, notice the equation that I derived is this: dy by dt equals minus 1 by tau into y, right? I just took this term to the LHS. RHS is 0, right? You can have a non-zero RHS. You can have some other function as a forcing term. In fact, breathing, exhalation, you have a resistance and compliance, right? Inhaled, you know, there is some volume of air in this thing, and then the lung is discharging. That is unforced. The moment you put a ventilator, typically you are actually forcing. There is a forcing function involved. Okay, the way to deal, the actual tool to deal with it is known as Laplace transform. The moment you know Laplace transform, you can deal with all this. You know, you can deal with the step function, impulse function, ramp, and all of that. Another class of very, very, very typical RHS type of RHS function is sinusoids and sinusoids. What happens if I excite it oscillatorily? Even in, I think, biomaterials, biomechanics, I said creep recovery, one experiment we do, relaxation, one experiment we do, then we also do oscillatory shear, right? In electrical circuits, this is, hey, I have an AC voltage source. What happens to the current and voltage in the RC circuit? Sinusoids. If it's not a single sinusoid, hey, the ventilator forcing function is actually a complex function, but it's periodic. If we can, again, deal with one sinusoid, okay, this is a complex function, but it's kind of periodic. You can split it into sinusoids. This is essentially, Fourier series, periodic function, right? Summation of sinusoids. If you know how to deal with one sinusoid, you can actually, things are all linear. Fortunately, you're working in that range, certainly from a gate perspective, right? Do superposition. If you know how to deal with one sinusoid, you know how to deal with the summation of sinusoid. Notice any periodic function can be split up into summation of sinusoids, right? That's a Fourier series. Even if it's non-periodic, actually we know how to do it, right? That's a Fourier transform. So bottom line, one class of non-zero RHS forcing function is a step function, impulse function, ramp function. There is a voltage, DC voltage source. You are not blowing out against zero pressure. You are actually blowing out against non-zero pressure, let's say from the ventilator or something. Or the second class of famous forcing function is sinusoids. In fact, I mentioned sometimes CISO, sinusoidal input, sinusoidal output, right? Have a sinusoidal input and look at what happens to y of t. Y of t again will be sinusoid, but it will have a different amplitude and phase. That is typically studied using tools from frequency response and Fourier transform. But notice these are slightly advanced generalizations, but even till here, if you want to do well in the gate examination, you are supposed to know this. You have sufficient time for that. Okay, you cannot do this in a 2-hour sitting, but these are all doable. Okay, and this is where the connection with actually S&S actually shows up. And systems, right? This is the place where S&S connection actually shows up. And no one told you this variable unit of t has to be time. Unit of t can be distance. What we are actually dealing with could be this equation. Make it some other constant. Okay, let's make it tau itself. Okay, y. Now your y is a function of x. Distance, typically x. This is distance. X is not time. You have a space variable instead of a time variable. Function of time instead of that you have a function of space. Hey, are these things there in the gate syllabus? Yes. Fourier attenuation. Intensity case exponentially in space. Radioactive nuclear decay we already discussed, right? Initial radioactivity or count. Okay, after some time, the count decreases exponentially. In probability, notice is also there in fact some of the tools in math, engineering math will be useful, specifically exponential distribution, lambda e power minus lambda y, where y is a random variable, right? The specific reason to actually mention that is, the mean of this distribution is 1 over lambda. So what is a mean life? Half-life is one thing, we derived this thing. What is a mean life of a nucleus? You know the answer, that is actually 1 over, mean life will be 1 over lambda. That is one thing. In terms of, this is in time. Y can be space or probability variable, can be anything, random variable, space, time, need not be space, time. Okay. In X-ray attenuation, things are in functions of space. For example, there you have again an attenuation coefficient. It is not written in x by mu format, but it's, by convention, it's written as mu x format. And then there is here we had a half-life, there we have a half value layer. Here we have a mean life, there we have a mean free path. Does it stop there? No. Again, in ultrasound attenuation, the amplitude of sound kind of decays exponentially with distance, space. There are some subject-specific units here, like neighbors and decibels. There are places where this decay is exponential, but not, the base is not naturally. Base 10 is used and all that, is, for example, Beer-Lambert, but same decay shows up again and again. So same related parameters. In fact, what I am showing in this figure can technically be dealt with. Forget this generalization. Whatever we did till now, if you replace time with space, you already know this details in the table. So you already know X-ray attenuation, numericals pertaining to that, ultrasound, sound attenuation. You have seen, right? I already mentioned that mean of this probability distribution is 1 by lambda. Radioactive decay, of course, you can deal with it. Radioactive decay, tissue culture, bacterial growth, decay, and all that. So if you take an RC circuit, if I apply a voltage or a current here, what will be the voltage or current here, right? Typically you apply voltage. Say if I apply a step voltage, I suddenly increase the voltage here, but the output doesn't suddenly increase. Output only, capacitor only gradually notice increases. This is what we studied. Now, in fact, I have a non-zero forcing function. Suddenly step response, the capacitor gradually charges. Okay, this is saturation. We'll in fact will connect to that. We'll look at this separately one day, but that is slightly more advanced. Okay, but we'll look at that separately, specifically with u of t. Okay, this curve is what we studied today. Notice the 0.63 and all that is showing up right at tau. Curve is what we studied today. This is used to, you have any sensor, what is the input, what is the output. The sensor is typically characterized using what is the step response, what is the frequency response. Okay, now if you have a sinusoid here, this will be a sinusoid. What happens to the amplitude and phase of those output sinusoid with respect to the input sinusoid? Okay, this is known as frequency response. Again, this is fairly easy. Notice what I have. This is, the approximations are Bode plots, right? The straight lines here are Bode plots, frequency response. This is there in signals and systems as well as controls. Okay, these are some of the basic things. Specifically, the generalizations you still have time to learn, and most of you could learn. We'll also discuss this. If possible, I'll try to have class like this, session like this to discuss that. But if we really want to excel, differential equation is first order, dy by dx. Highest derivative of y is 1. Highest derivative of y can be 2. That is referred to as a second order system. If you want to excel, this is what you're supposed to do. Of course, this is all covered in the recorded lectures. Time permitting, we'll try to discuss, time and interest, time permitting and interest allowing. We'll also discuss some of this second order characteristics. Okay, same thing, sensors, this shows up second order. Most real world systems are second order systems. Okay, you have an inductor like effect or a mass like effect. There is kinetic energy like term. Okay, you need to account for that for everyone. Okay, second order systems. But till this, I suggest all of you should know sufficient non-biomedical knowledge, understand non-zero forcing function, step function, how to solve that using Laplace function, how to analyze that using Fourier transform, how to do frequency response analysis and all that. This much knowledge is certainly expected. Okay, but we'll do it slowly. What we did today itself actually a lot. We did today, given any 3, you can find the other. You can find that from a table, you can find that from a figure, you can find related parameters like half-life and all that. So, okay, given any 3, either t, tau or the related parameter and 2 other things, you can find the other. It need not be a time variable. I just pointed out it's a space variable. With this itself, you can technically answer 3 to 4 questions. Okay, 3 questions on an average. If you're lucky, 4 questions. 1 or 2 advanced questions are there, typically from second order, or they probe you a little more. Okay, from typically from a second order system. Okay, so this would be a good place to stop, unless any questions I'll address, but this would be a good place to stop, right? And my point is, you understand the concept, and if you appreciate how and why it shows up, the same thing shows up in different subjects, that makes it so important. In that sense, if you learn this one thing, actually you can answer so many questions, right? That also gives you this motivation to learn it properly, right? If we show it to you in this way, right? Typically, if you are doing a medical imaging course, you are learning this. If you are doing a circuits course, you are learning this, right? This connection is not seen. Perhaps if I show it to you, the commonality among all these things, this way, my hope is that you learn that, you understand that better, and you learn it better. Hopefully that happens. Okay, that happened to a large extent. Anyways, this is recorded. I'll make it available if you want to view it again and get back to this. And from gate perspective, this is one of the most useful 2 hours that we have spent. Okay, any questions? Let me stop the recording. I'll answer a few questions and then we'll wind up. Okay, so let's stop. This is being recorded, right? Yeah, stop recording.